Okay, last time we had written down the expression for Hamiltonian and also the momentum operator for this system. So let me write it down again. So we saw that we can write the Hamiltonian as d cube k omega k a dagger k t a k t. And remember, there was another piece which was an infinite constant which we have dropped. Okay, and I gave you the reason for that also in the last video. And we have guessed that we should have an operator P which should have this form. And of course, I am going to come back to this in much more detail later. But for now, it's a good guess that we have. Okay. So, this is something familiar to us. We saw already in the beginning of this course that we can write down the Hamiltonian as a system of independent harmonic oscillators. Okay. So, this is exactly what you get if you use the variables a dagger and a for writing down the Hamiltonian of a simple harmonic oscillator. And each oscillator comes with its own frequency omega k, and now you have a continuous set of oscillators. So, k is continuous. So, you are summing over all the oscillators, k is continuous. So, omega k is also continuous, and the different oscillators do not talk to each other. They are really independent, because you see there is no term in this Hamiltonian which couples oscillator with k with another oscillator with k prime. Okay, so these are all independent oscillators, and this is what will happen in every field theory, every free field theory which you will study. Okay, you will always be able to write it as a sum of harmonic oscillators, and that's always going to be your starting point when you are going to do perturbation theory for non-interacting fields, for interacting fields also. Anyhow, I want to make a remark here, or maybe two. Our Lagrangian that we wrote for this system, that does not explicitly depend on time. Okay, Lagrangian does not depend explicitly on time. So, here the emphasis is on the word explicitly. You see, it depends implicitly on time through the coordinates. So, to understand this, what you can do is you can again go back to discretized version of the Lagrangian. Okay, in that case, you will be able to write it down as a sum of the coordinates qi, which we have seen that we can write as h3 by 2. H is the volume, the length of a cube. So, the three sides are h, h, h. So, the h cube is the volume of each cell when you have quantized the space. Okay, and then phi I is the discrete version of the field. Okay, this is what we saw. And when you write down the Lagrangian using the QIs, which I have written down here, so this of course depends explicitly on time, you will see that the time dependence is always through phi I. There is no explicit time dependence anywhere. Okay, phi I or pi I. If you are looking at the Lagrangian, of course, there is no pi, it's just phi's, okay, and phi dots. So, which implies that this is 0. Okay, there is no explicit time dependence. And we also know that if Lagrangian does not depend explicitly on time, then the Hamiltonian also does not depend explicitly on time. Okay. Okay, that's good. Now, we have the Hamiltonian here, which has a dagger kt, a of kt. Now I am going to I want to find out how these operators evolve with time, the operator a, for example. So let me first treat it classically, and then I will quantize it. Okay, so if you recall, you have learned in classical mechanics that if you have any function u of coordinates, okay, and momenta and time possibly. So let me write q, p, and t. So p is the conjugate momentum. You could have several qi's. So I'm suppressing the indices pi and qi. Okay. Then if you ask for a total time derivative du over dt, okay, then if you use equations of motion, the canonical equations of motion, okay, which are let me write down here, which are q dot if you use these canonical equations of motion, okay, using this you can write down the total derivative of u as the Poisson bracket of u with h, that is correct, plus a partial time derivative of u with t, because u could possibly depend explicitly on time. Now if I assume that there is no explicit time dependence, then this drops out. Okay. If u is not explicitly dependent on time, okay, if that is the case. Now let's go to quantum version of this. So if u is an operator, if I promote u to an operator, so it goes to u hat, h becomes the operator h hat, then you know that the Poisson bracket u h, it has to be replaced by the commutator with a factor of 1 over I h bar. Okay, sorry, here I'm sorry, u is the commutator here, 1 over I h bar. Okay, that's the prescription, right? See, the Poisson bracket is I h bar times the commutator is I h bar times the Poisson bracket. So that's what I have written here. So if I go to quantum theory and I work in Heisenberg picture, where we the entire time dependence is carried by the operators. Okay, and if you you work in Heisenberg picture, which I want to work with, okay, and if you have an operator u, then you will have du hat over dt is equal to this Poisson bracket gets replaced by 1 over I h bar times the commutator of u and h. Okay. So I will use this and try to calculate what a k of t is, how it evolves with time. Okay. Now see, your a is not explicitly dependent on time, the operator a. So if I write the same equation above, so I will not put a hat, it's obvious that we are looking at the quantum version because I have a bracket to remind us that. Okay. Now our a is not explicitly time dependent because it depends on the pi's and phi's, and the time dependence is through them. So I don't have a del a over del t piece here, and I can just calculate this commutator to find out what should be the right hand side. Okay. And that's easy because the h you have is in terms of a and a daggers, and we know the commutation relation of a and a daggers. Okay. The only point here is that when you are substituting for h in this expression, okay, let's be a little bit more explicit here. Let's put, sorry, let me put the indices properly, not indices, the arguments. K T is equal to okay. Now this h, if you go back here, has a dagger kt, a kt. Okay, but this t could be different in principle. You could put t prime, but because this is time independent, I can choose the time which you have here, same as what you have here. Okay, then all is good. So you can just now use the commutation relation which we have seen earlier. Let me show you again if I find it easily. Yeah, here a dagger is h bar del cube. Now I will put h bar to be 1. Okay, so that one you can use and arrive at the following. So here is a very simple exercise for you. You can show that dA kt over dt is 1 over I h bar omega k a k t. Okay, that you can show. All you will have to use is this thing. Okay, this if you use, you can arrive at this result, and this is easy to find the solution. It's easy to find the solution for this equation. Remember, a is an operator here, so a k of t I can write down as e to the minus I over h bar omega k t, and we have a constant piece a k of, okay, not looking nice, k of 0. Okay, and this thing I will define to be a k. Okay, so that's the solution, and we will not keep the h bars. In fact, I noticed that I have not been very careful in or being consistent in keeping h bars. So somewhere here, yeah, somewhere here I was not very careful. But anyway, at least at the places where I was writing commutators, I was writing h bar properly, and at other places I was putting h bar to be 1. But if you put all h bars to be 1, it will be good. So there is no mistake as such. But yeah, it's not nice that I missed at some places. Okay, that's good. So we have a k of t is e to the minus I omega kt. Okay, and a dagger, okay, I'll put h bar right now, but not later. Okay, omega k t a dagger k, where a dagger k is just the Hermitian conjugate of this one. Okay, that is good. Now it's clear that if you write down the Hamiltonian, there will be no time dependence left, because this and these are complex conjugates, so they will just cancel. Okay, and you are left with only a dagger k, a k. Okay, so it's manifestly there is no time dependence here. I can also use this result, these two, to write down the expression for phi. I am putting x without a vector, which means it has both the x component and the the time component. So when I write x without a vector, I mean the following. Or even better, this is what I mean. Okay. Now let me go back and show you. Yeah, here. So we have d cube k over 2 pi 3 halves 1 over root 2 omega k. The a k t we have now written as, this piece is now a of k, and the time dependence is what? E to the minus I omega k t. Okay. Now if I combine it with this one, this exponential, in the exponent you will get e to the minus I, and in the brackets omega k t minus k dot x. Okay. So here you will get this, combining this, e to the minus I omega k t minus k dot x. Okay, from here. And this piece, it has e to the minus I k dot x with 3 vectors, and it has a dagger which will give you e to the I omega k t. So if you pull out I omega k t, okay, you will have here e to the I omega k t minus k dot x. Okay, that's what you'll have. So you see, these two are just complex conjugates of each other. Okay, so I will have an a k e to the minus I omega k t minus k dot x, and here you will have plus a dagger k e to the I omega k t minus k dot x. Okay, so that's what I'm going to write there now. Yeah, let's see if I can remember correctly all the expression. 2 pi 3 halves, then I had a 2 omega k in the square root, that's correct, and then I have an a of k e to the minus I omega k t minus k dot x. Looks like everything is fine till now. A dagger k e to the I omega k t minus k dot x. Okay, so I have used equations of motion in writing this phi of x, right, because this relation is coming because I have used equations of motion. Remember, I use canonical equations of motion in writing down what the time derivative of A is, and that is what I have plugged in here. So equations of motion have been used in writing down the phi. Okay, that is good. All C and H bar have been put equal to 1. Okay, and also remember that here in this expression omega k is, as before, k square plus m square. Okay, that is also good. Okay. Now, I hope you have noticed this, but let me say anyway. So note that we have e to the minus I omega k t minus k dot x. Okay, that is with A, and the other one has e to the I omega k t minus k dot x. Both have the same, apart from the minus sign, they have the same thing. Now see, if you write k mu as k omega k, which is the k0 k vector, okay, this is a 4 vector, right? Now x mu is also a 4 vector. So both these quantities transform as a vector. I can construct a scalar out of them, k dot x. I am not putting vectors because I imply a 4 vector, and that k dot x would be omega k t minus k dot x, right? Which means that what you have in the exponent is a scalar, a Lorentz scalar, right? Because that's what dot product of two 4 vectors is. It's a scalar. So you have e to the minus I k dot x. Okay, when I am writing k dot x without any this thing arrows on the top, it means dot product of 4 vectors, and the other one is with e to the minus I k dot x. Okay, and it nicely shows that these exponents they are Lorentz scalars, which they should be, otherwise it will have a weird transformation. So phi of x is now d cube k over 2 pi cube omega k, and then we have a of k e to the minus I k dot x plus a k dagger e to the I k dot x. Okay, this is fine, that's good. You should also be thinking like, I mean, I've been saying that phi is a scalar, phi is a scalar. This part is okay, transforming properly. How about the other pieces? Do they transform correctly to form a scalar? Okay, that is one question which should be on your mind now, but I will leave it for now, or maybe most likely I'll give it as an exercise. Okay, so this is one thing I wanted to write, and let's also record what pi of x will be, the momentum density. And remember, pi x you can of course substitute in the expressions that we wrote earlier, but if you recall that pi x is just phi dot, okay, then it's easy to see that if I take a time derivative, it will pull out a minus I omega k here, right? So it has a omega kt, so that will pull out a minus I from this one, and if I take that factor out, okay, I will get a minus I here. This one, when I take the derivative, it will give you I omega k, and because I have pulled out a minus I, there will be a relative minus sign. Okay, so let me write here a of k, then of course you get back the exponential and you have a minus sign, and because you are pulling out minus I omega k, this gets changed to omega k over 2, the square root. Okay, and then this is a dagger k and e to the I k dot x. Let's see whether everything is correct here. Yeah, all is good here. Okay, this is nice. This will be for our later use. Now we will, in the next video, start looking at the states in this free theory. Okay, so see you in the next video.